Hello and welcome to the Getting Started talking about integration of µRTE. My name is Thomas Barth and I'm the creator of µRTE. In order to integrate µRTE onto a particular target, there are a few interfaces required. So µRTE makes use of an underlying operating system. So we need to establish the interface towards this operating system so that µRTE can use its services. And in addition, we need certain services like in the current implementation, a timestamp source, which later on will be used to calculate signal ages and similar. And we might want to integrate drivers to perform checksum operations. In this example, I'll show the integration onto an Infineon Aurix generation 2 and an high-tech PX ROS. Because µRTE is not aware of which operating system is used on a particular target, tasks modeled have to be created manually. So in this particular case, we have 3 tasks which have been created in the model, and those tasks now have to be created manually by the user. It has to be ensured that the task stack is linked to the same section as it was defined in the manual. If the target and the operating system support memory protection, we have to make use of the memory protection set for this particular task. So µRTE will automatically generate the protection set for this task. And in the task body, we have to invoke the static run method of the corresponding task as it was modeled. In addition to the application tasks, there is one system task in which the so-called central activation engine is implemented or integrated. Here we also need to make sure that we link the stack to the same section as it was defined in the model. We have the memory protection set, and also here we have to invoke this static run method. Before operating system start, it is highly recommended to invoke this init pre-OS time method of the central activation engine, which will initialize all the internal data of µRTE. And not only that, also for global data objects such as signals, which theoretically should be initialized by the startup code, especially on embedded targets. This sometimes can be a little tricky. So this method will also make sure that all the signals and all the global data signals are initialized to a defined state. In this example, the code was generated using the default folder structure, in which the basic integration onto the target and the error handling is located in source RTE config, and I will now go through the files in there step by step. Within µRTE config error handling, there is the internal error handling of µRTE. So whenever there are internal errors, and we now have to separate that from application errors, those errors are really like internal of µRTE, then the user can define what the reaction of the underlying system should be on that particular error. Because, for example, here for the first one, what to do if a periodic event triggering a task or could not be allocated. Something like that cannot be decided by the µRTE. So the integrator here has to decide how to react on such an error. Depending on the error, certain meta information is given. So for example, in that case, the ID of the task which tried to allocate the periodic event and the event handle. But because those those error handling hooks are implemented as macros, the integrator has quite some flexibility on also gathering other status information and being inside of the logic and the context of the internal RTE code to make the error handling as good as possible, especially in high availability systems. Within µRTE config memory.h, we have the memory interface. So first of all, here you'll find all the symbols as they have been defined also in the generated linker description file. Then we have the protection sets from point of view of the task. They come in two flavors. They come more or less standalone, so only the data they are assessing. And they come as a version where they also have the stack reference as it was defined in the model. This now depends on the operating system which is in use, if the protection set also shall include the operating system stack. So this one is for the system task, the central activation engine, and this, for example, is for an user task, so a task activation engine. And in here you'll find, for example, that this task obviously needs to have access to its own metadata, but also in that case now to periphery, which is an LED. And once again, it comes in two flavors. Also in here, we find memory protection sets. They work a little different. They are from the point of view of memory. And for one particular memory module, so for example, in that case, this is the data scratchpad memory on core 0. For this particular memory, we'll get a list which task is assessing which area within that memory. And this comes in two flavors. This one was task-based, this now is core-based. So basically the same story, but in that case we can see for a particular memory which core is assessing in particular memory area. Because µRTE is not aware of the format which is expected by the operating system or driver who want to process this data, there's an intermediate abstraction layer here in between, in which the user or the integrator has to define the system specific format for memory protection entries. Next, we will have a look at the operating system configuration. We have a header file in which we have to define things like the there is an intermediate data type, for example, in this case for what is an OS task. In this particular case now, this here is this µRTE object. For free RTOS, this, for example, might be a task handle. We have to define the initial values for those data types. Here we have to define how to compare two of those task types. We have to define logic on how to get the current context of the operating system, and so forth. Yeah, so events here, for example, and this goes on and on. Yeah, so you basically have to check all of those entries here to make sure they fit with your operating system. In the .cpp file, this is a little different, because in here we have actual user code, and this user code in here is responsible, for example here, to transmit data from one task to the other. So for example here, for this function, we get a receiver task, the signal which has to be updated. So in that case, this is a signal update process. The event which is associated with this signal update process. So for example, do we have new data? Is there an error? we get a pointer to the signal and the size of the signal, and our job here now is to gather all this information, make in this case now a message, in pxROS message out of that, and send it to the other side. We have to do this once for regular context, then for the ISR context, which in this case is not supported by pxROS. In here we have to define how to send triggers from one task to the other, and then on the bottom we have to define the logic on how to extract the message that now was received on the receiver side to get certain meta information out of that again. The best way from my perspective to understand it is to go into the code of a task activation engine and then go down to this wait next event, in which the logic which was defined in the header file of the OS configuration and also the code is referenced from here, and then simply step by step go through those symbols as they have been defined in the configuration to understand what it is doing and why it has to be configured. Next we have the so-called state handler. And the state handler is a method of the central activation engine and is also executed in the context of the central activation engine whenever a runnable which can return a value, so this is configurable if a runnable can return a value, returns a value other than OK. Then we have this centralized state handler which is now processing this information. So the idea here is that this state handler, now it's a mixture. It can respond to this event in terms of application. So it's maybe changing the current system state. So once again, the system state is defining the data flow of the system. In order to decide what to do, we get the current system state and we get this package or the structure here which contains meta information about what has happened, and we now in here have the possibility to change the system state based on this information. It's processed also by the central activation engine because there's a queuing mechanism integrated in that. So if we get multiple so-called state change requests, they are processed one after the other. Why this is also important from the integration point of view, because this could be now an interface to escalate application errors towards the underlying hardware or the underlying system if such errors or the error values reported by the application cannot be handled by state changes. Also down here we have the run deadline handler. There is a feature of µRTE in which the runtime of runnables can be measured, and if the predefined worst case execution time for a runnable is exceeded, then this this function here is called. Within the µRTE config CPP, we'll find mainly lookup tables which allow debuggers to translate things like function pointers or enumerations back to strings. So there is no user code in here other than in this µRTE config.h, where basically the type definitions for the runtime environment are located. So we have this this very widely used µRTE return type, which consists out of a few internal values, a few predefined values, but the user can also extend that by own values. We need to define what is a null, we need to define what is an unsigned 8, and so forth. But what's also in here is the acquisition of the signal time. So what data type do we want to use as a timestamp. So all the signals in µRTE have a timestamp from which the age of data can be calculated. So we have to define a data type for that. And we also have to define, I'm sorry, how to get the current timestamp. We have to define for the task activation what kind of, so for example in that case here we have a bit mask for tasks events. Here we need to configure which bit in this event mask has which meaning. If we want to use checksum features, we have to define how to calculate the checksum and so forth. So once again here, because of the number of possible parameters, it makes sense that you on your own go through this file step by step and also check the references of the code in here to understand within the context where it is used and what it is doing. All right, that was the overview of µRTE integration onto a particular target. My name is Thomas Bard. Have a nice day. Bye.